Hello, good afternoon, everybody. Welcome to session 5, Application and Internet of Things. Our first paper will be Deep Learning-based Embedded ADAS System. And this paper will be presented by Frederico Souza.
Hello, my name is Frederico, and I'm from the Federal University of Ouro Preto. And I'm going to introduce you Deep Learning-based Embedded ADAS System. So, an ADAS is an Advanced Driver Assistance System. So, it is a system designed to alert drivers to traffic conditions that
Ô, Matheus, eu não estou ouvindo, não.
accidents or potential accidents. So, we have
o som é controlado por cada pessoa, professor. Se aumentar o seu som, talvez você consiga escutar. Ou...
Os outros estão ouvindo aí, pessoal?
Estão ouvindo.
Ué, o meu tá no máximo aqui. O meu áudio está no máximo.
Tem um controle no próprio player que está aqui na conferência web. Eu não...
Visual and audible signals that can be raised to alert for nearby vehicles, pedestrians, or objects on the driver's blind spot. The complexity of the traffic environment requires high processing and precise sensors and actuators to be able to produce real-time alerts. So one of the main sensors used in ADAS applications are cameras, due to the low price compared with other sensors like lidars and the ability to capture all environment details. So cameras can act as the vision of the system. So usually we have cameras as the main sensors to capture the details of the environment. So when using cameras, we can employ certain techniques as image processing, and more specifically, we're going to use in this work neural networks to process and detect relevant traffic information, such as we already mentioned. And it's also one of the objectives of this work to make an approach that can run embedded. So we use and evaluate this application on 2 NVIDIA boards, that is the NVIDIA Jetson Nano and the TX2 board. These 2 boards are good for these applications because we can use their GPUs to increase inferencing time on deep learning models. So we have these, we're going to validate this application in these 2 boards and compare the performance in both of them. So here is our methodology. And to analyze the traffic environment, we train 3 deep learning modules. We have a object detection model that detects other vehicles, persons, and road signs. We have the lane segmentation models that segmentate the road lanes and detect the position of them. And the road sign classifier that classifies the speed limits of the road based on the road sign detections by the object detection model. The lane segmentation model. So we trained 3 lane segmentation models based on 3 different backbones of the ResNet backbone. That is the ResNet 18, the 34, and the 50. The basic difference in these backbones are the number of layers presented in their architecture. So we also applied this backbone on a UNet architecture with an input resolution of 384 by 384. So to train this model, we merged two public data sets. That is the ToSimple dataset and the QLanes datasets. They are already labeled datasets that make training a lot easier. So this is how we've evaluated our lane segmentation models on these different backbones. We use the frames per second metric on our both boards to evaluate the model, and we also use accuracy to evaluate them. As we can see, the ResNet 18 model had the best results regarding the frames per second, and the accuracy does not change a lot. These results on the frames per second were obtained through an inferencing process that we're going to explain further in this presentation. And as observed, more complex backbones with more layers achieve a significant FPS loss with little accuracy gain in our case. This accuracy might seem low, but this happens due to occluded adjacent lanes in the validation dataset. In our ADAS approach, we are only interested in finding the vehicle's current lane. And as the next figure will show, this is actually satisfactory to us, to our application, the accuracy of the model. So here we have the comparison between the ground truth, the ResNet 18, the ResNet 34, and the ResNet 50, between the predictions and the ground truth. As we can see, we are detecting the middle lane of the car very well, and this is the main aspect of our implementation. The object detection model is a model made available by NVIDIA team, and it's called the Traffic CanNet. This model is trained on a MobileNet V2 backbone and has an accuracy of 83%. This model detects cars, two-wheeled vehicles, persons, and road signs. This model, we used it specifically because it is optimized for NVIDIA platforms, because it uses TensorRT and is available on the DeepStream framework, which is a framework that enables fast inferencing in the L models through TensorRT and also GStreamer that is a part of this framework. We're going to go on a little bit of these details further on the presentation also. So we have finally the road sign classifier. So we produce the data set, our own data set, with 71,000, more than 71,000 plates collected from Brazilian roads on different scenarios. We also trained it on a ResNet 18 backbone, and it has 13 classes of 10 kilometers per hour, 20, 30, 40, 50, 60, and so on. And also the others class to classify other types of road signs. We're going to talk about the inference workflow, where is the main aspect of our approach. So the inferencing process, we use DeepStream that we already mentioned. That is a framework based on GStreamer. GStreamer is a fast video processing library. So on the DeepStream GStreamer logic, the neural networks are components of the stream pipeline. The stream pipeline is the pipeline where all the frames flow through on GStreamer. The neural networks are started in a plugin called NVInfer. The NVInfer instance receives a TensorRT engine. This engine is a version of the model on a TensorRT optimized inference engine. So you train your model normally, and then you put it on a TensorRT engine, and it's optimized for the DeepStream framework. And it can accelerate the video processing in this neural network on NVIDIA hardware, of course. So all the data extracted from the detections of each model are accessed and processed. So the lane detections and distance from each car are calculated. And this process repeats 12 frames. Here we have the road extraction pipeline. Where in one, we do a ROI extraction. This ROI extraction is based on a manual calibration. We set those points in red manually, and then we extract the region of interest where the lanes are. So after that, we get the metadata from the neural network, which is the segmentation mask, as we can see on 2. On step 3, we warp the perspective from the segmentation mask to have an upper view of this lane. And then the road lane coordinates are estimated on the segmentation mask, and the lane deviation calculation is based on the proximity of the vehicle's wheels to the right or the left lane. So we calculate the deviation from the center of the lane based on those two red points as the tires of the vehicles, or the wheels, of course. And then if it gets too close of the left or the right lane, we give in value to classify a lane deviation or not. So the distance estimation from front vehicles. On step 1 of this process, we calculate the lower center point of each bounding box of the surrounded vehicle as the red dots on the image, and then we estimate the real distance based on a camera calibration process. So this camera calibration process is a manual calibration process which consists of finding a regression relationship between the number of pixels and the distance from a known object. So we make a regression of these distances and we find the real distance based on this. And we got some experimental results here. And we propose 2 tests to evaluate the application, and these 2 tests vary on the resolution of the object detection model. This resolution decrease is not a retrained model. In the TensorRT engines, you can decrease the resolutions and generate different inference engines of the same model. So we don't need to retrain a model to redefine its resolution. And we use the mean IOU as the metric to evaluate whether the detections are dropping too much to an unaccepted value. So the following tests that we're gonna present are all the 3 models running on the application. The test 1, we use the resolution of 2024 by 2024, and this is the hardware consumption. So the GPU use are in red on the Jetson and on the left, and the TX2 on the right. And we can observe that on TX2, we are bottlenecking the GPU. The GPU on TX2 is getting more idle, as we can see. And this is due to a frame trade between CPU and GPU. And this is the frames per second obtained on both of these configurations, on Jetson Nano and TX2. As we can see, we got a mean of 15 FPS on Jetson Nano and a mean of around 27 FPS on TX2. As we can see here, on the resolution of 640 by 4080, the hardware consumption on TX2 increases the GPU use and decreases the CPU use on the TX2. On Nano, it's practically the same usage, hardware usage, but as we will see on the next slide, the frames per second will consider a drop. As we can see here, the mean of Jetson Nano is 11 FPS, while the TX2 is 25 FPS. But then, with the increase of resolution, we got to use more of the GPU, but we got less FPS. This comes with a price in performance as well. So these are some common errors when decreasing the resolution at the drop that of our tests, as in above in the upper image. We have the model resolution on 2024 by 2024, and below we got 640 by 4080. It's a more accurate, as the mean IOU metric suggested to us. As conclusion, we presented and evaluated this ADAS application. These are images of this application running on embedded hardware, and as you can see, it's feasible and it works. So we presented this application that uses DeepString 5, and our tests showed that with an input resolution of 2024, and we achieved a mean 15 FPS in Jetson Nano and 27 FPS on TX2. The other test showed that with an input resolution of 640 by 4080, the results obtained were 11 FPS and 23 FPS on TX2. Some future work here, we consider that we need to improve the system need for calibrations. As we saw, there are calibrations on distance calculation and to get the lane ROI, which can be improved. And improve, of course, the deep learning models to get higher accuracies, which is important, and implement the vehicle speed measurement through GPS. With the vehicle speed, we can judge whether the driver is above the speed limit or not, and also improve the alerts to collisions, to potential collisions. Well, thank you. This was our presentation.
Great. Thanks for the presentation. Is Federico here to answer the questions?
Yes, I'm here.
Okay, great. Do we have... Marcio is asking a question here.
Yeah, I was gonna type on the chat, but I'm gonna answer right here.
Yeah, just let me read it before, so that
Okay.
for object distance detection, what are the difference between using image processing approach as in your work and a solution based on radar?
Yeah, well, a radar solution would considerably increase the price of the applications, as we can see more lidars sensors being applied in these applications. We chose to an image processing approach to reduce costs. So but the basic difference would be a higher precision on this distance calculation, but it would also increase the cost of the application.
Great, thank you. Do we have more questions from the audience? I have a question. At the first slides of your presentation, you mentioned precision for the lane detection model. How do you measure that precision? It's around 60 something percent.
Yeah, it's 66%. We measured through. It's like when you have the masks, the detection masks, you can see how much they are overlapping each other. So we measure the accuracy through that. The accuracy I said in the presentation was low because our model was good enough to measure to predict the lanes on the current vehicle lane, but our data set had multiple lanes, so that's why it decreased a little bit. But as we see on the evaluation slide, the current vehicle lane is it's all right. We have to improve this model, but it was feasible to our application.
I'm not sure if I understood. You just get the ground truths. You compare your ground truths with the model output, and then you get the difference between the pixels.
Yes, that's it. Between the
Okay.
detection masks.
Okay. Okay. Thank you. Do we have more questions from the audience? I have a question. With when you varied the number of frames and also the resolution, and we used two hardware platforms. One is of different processing capabilities. Which do you think is the best trade-off? Because I think if you decrease a lot the resolution, you will have frames, but you also have errors. And if you increase the resolution, you have less frames, but probably your model will be more accurate. So I would like you to discuss a little bit the trade-offs between these two variables.
Yeah, well, this comes from you have to choose this trade-off based on price and your real-time real-time processing requirements. Higher frame rates. We first on this application we started using Jetson Nano to do everything, and we found this optimization, let's put it like that, to be able to process things on more faster because of the higher frame rates. Once we get to the TX2, we could experiment a little bit more on different resolutions and see how the things played out. As we can see on TX2, we achieved like 25 FPS on higher resolutions, and it's the ideal world. But it's also a more expensive platform. The TX2, it's considerably more expensive than Jetson Nano. So it's basically a real-time constraint. Like if you need more frames, you'll have less precision, but you'll have something that's running like on a real-time perspective, like 15 FPS. As we researched, it's something that it's feasible on real environment. But if you, I don't know, maybe do it on the cloud, let's say that, you can get higher and higher frame rates based on more GPU power, of course. So that's the trade-off. Is, I would say, it's not only on resolution, it's also on your price range and where you want to run this application. Because with better GPUs, you will get better accuracy and better FPS also.
Great, Federico. Thank you for the presentation, also for answering the questions. I think we can move now to the second paper of the session. The paper is a parallel software-defined ultra-low power receiver for satellite message forwarding system. This paper is going to be presented by Diego Cirilo do Nascimento.
Hi everyone, my name is Diego and I'm going to present the paper entitled A Parallel Software-Defined Ultra-Low Power Receiver for a Satellite Message Forwarding System. I'm one of the authors, along with Rafael de Lima, José Marcelo Duarte, Reinaldo Filho e Samuel Xavier de Souza. This is our agenda for this presentation. In communication systems that require data collection in remote areas, the solution that has the lowest structural cost is the message forwarding system based on low Earth orbit nanosatellites. In this type of system, satellites act as intermediary stations. They receive messages from users, also here called platform transmitter terminals, and retransmit to receiving stations. Finally, a data distribution center offers a cloud service so that the customers can access the data from its transmission platform. The Brazilian Environmental Data Collecting System, Argos and Global Star are examples of such systems. Satellite communication systems have been replacing large satellites with several small satellites in the CubeSat standard, forming what's called a constellation. The CubeSat standard defines one unit size as a cube with 10 cm edges and a weight of 1 kg. The ISIS platform provides in this configuration an average payload power of 400 mW and maximum power of 2 watts. It's possible to combine units to obtain larger nanosatellites if necessary. This standard adopts the use of commercial off-the-shelf components. Due to its dimensions and weight, the cost of launching nanosatellites is significantly lower than compared with large satellites. The use of COTS components eliminates the risk of trade embargoes, reduces the cost, and facilitates application development. In addition, COTS components have greater performance than components that have spatial qualification. As a drawback, COTS components are less reliable. Although nanosatellites are cheaper due to their dimensions, this limits the availability of energy for their subsystems, creating a critically energized environment. Two projects motivated this work, the EDC project and the Severo project. In order to update the Brazilian SBCDA system, the National Institute of Space Research, INPE, launched the EDC project, a signal receiver based on a hybrid architecture with processing split between an FPGA core and a single-core processor. This receiver is scheduled to be launched in the constellation of nanosatellites CONASat. With onboard signal processing, the EDC eliminates the need for a dedicated transmitter and can use the transmitter integrated into the satellite telemetry system. The Severo project aims to build a fault-tolerant hardware and software platform for aerospace applications. The project is based on the RISC-V architecture and the open-source Parallel Ultra-Low Power (PULP) platform. The main objective of this work is to offer a nanosatellite signal receiver digital module with maximum energy efficiency and compatible with the architecture of the next generation of processors for the aerospace industry. The transmission platforms that are part of the SBCDA comply with the protocol defined by the second version of the Argos system. The bit rate is 400 bps and plus or minus P by 3 PSK modulation with a Manchester encoding. Transmitters do not have synchronism and transmissions are periodic. Thus, the coexistence of signals over time is proportional to the number of system uses. It is estimated that on average there are between 5 and 7 signals overlapping time. The algorithm considers the baseband signal and a transmission rate defined at 128 kilosamples per second. The signal is segmented into 10 millisecond windows. Each segment passes through the signal detection module that identifies the presence of the signal through spectral analysis and a detection loop. If there is any active decoder, the decoding module processes the input segment. In this module occurs the signal demodulation and bit detection. After decoding is complete, the data is stored in an output buffer and the decoder is cleared to process new signals. The modulation of detected signals is performed by applying the matched filter. This is performed through a phase-locked loop. The PLL receives as parameters the frequency and amplitude of the detected signal. This frequency is corrected through a loop filter set to a maximum error of 10 degrees. The demodulated symbols, Q of n, go to the bit detection algorithm. The ideal sampling time of symbols should be calculated to avoid intersymbolic interference. For this, the feed-forward algorithm of order was used. This algorithm extracts the optimal instant from the calculation of the frequency response phase of the symbol rate change. A buffer with twice as many samples per symbol ensures a constant bit stream. The sampler performs symbol interpolation for bit detection. The Gapuino is a board that has a commercial GAP8 processor that was used to carry out this work. This development board provides pins for measure processor's consumption. The GAP8 processor has a core, the fabric controller on the left, which acts as a microcontroller unit, and 8 cores in a cluster used for vectoring and parallelizing algorithms. Fabric controller and cluster have independent frequency domains and power switches. The 8 cores of the cluster share L1 data memory and a single instruction cache. The parallel algorithm was implemented under the Pulp OS operating system. This OS uses explicit parallelism that uses functions to command which part of the code that will be parallelized. This kind of parallelism gives full control to the developer, who must be concerned about memory access by the cores. There are specific functions to control the voltage and frequency operating points for each domain. Due to the sharing of data memory and instruction cache in the cluster, the GAP8 architecture is more suitable for parallelism at the data level. Therefore, a flow of instructions and data classified as a single program and multiple data, SPMD, was used. This stream is based on single instruction multiple data, SIMD, without regard to lockstep. To define the points where the algorithm should be parallelized, a profiling of the sequential implementation was performed. The proposed architecture runs the entire algorithm in the cluster and a variable number of cores according to the processing needed. For the parallelism of the FFT, the maximum possible scope was considered. The 2048-point FFT is divided equally between the 8 available cores. Each core is responsible for calculating 256 butterflies in each of the 11 stages. The demodulation process takes place on demand. When the number of detected signals is greater than the number of cores, the process is divided into 2 sequences. The figure shows the processing of a segment, and there are 12 simultaneous signals. The 12 signal limit was imposed due to the memory limitations. A MATLAB script was used to generate 2 files to carry out the tests. One file containing the signals and the other containing the transmitted bits for validation of the implementation. The generated signals had a minimum size of 360 milliseconds and a signal-to-noise ratio of 43 dB. They were spaced in frequency and overlapped in time. Initial phase and Doppler rate were randomized as seen on the first table of this presentation. Processing time, power, and energy consumption measurements were performed by the Magic board, according to the diagram in Figure 7. Energy and power consumption considers the entire GAP8 chip. Measurements were carried out by means of complete transmissions with signals superimposed in time. The first tests were carried out comparing the sequential implementations in Fabric Controller and in the cluster, and parallel in the cluster for processing the transmission of one user signal. Table 2 shows the results of measuring the average processing time of a 10 millisecond segment. For the power and energy consumption, the measurements correspond to the processing of the entire transmitted signal. It can be seen that the sequential implementation of the Fabric controller failed to comply with real-time processing constraints, that was of 10 milliseconds. In the cluster, it is possible to see a performance improvement when we use the L1 memory. Even with a lower frequency, it already meets the real-time processing constraints for a user signal. Parallel implementation, in turn, has almost half of the processing time of the sequential implementation in the cluster. Processing time measurements show that the FFT consumes approximately 80% of the detection module's processing time. It turns out that to carry out the parallel implementation, it was necessary to reorganize the code and reuse memory for processing this block. These improvements could be made in sequential implementation. As for energy consumption, it is possible to observe that the use of the cluster increases the average processing power needed. However, the total energy of the parallel implementation is the lowest shown. Decreasing processing time here is critical to promoting energy savings. For processing more than one signal concurrently in time, the parallel implementation is the only one to meet the real-time constraints. The margin to meet the real-time operation presented by the parallel implementation allows the reduction of voltage and frequency operating points in order to promote greater energy efficiency. For this, a processing time threshold of 300 milliseconds was defined. The operating frequency was decreased so that the processing time of the signals orbited around this value. Voltage was reduced as allowed by the datasheet specs. As a result of this variation, a maximum reduction of approximately 43% in average power and 12% in energy consumption could be observed. This occurs when the number of signals equals the number of cores in the cluster. From an FPGA synthesis file provided by IMP, it was possible to calculate through the manufacturer's software the total consumption of the EDC SoC. Comparing the processing of 12 simultaneous signals of the proposed implementation with the value presented by the EDC, it is possible to observe energy saving of approximately 75%. This paper presented a parallel software-defined implementation of a multi-user PSK receiver in an ultra-low power processor for a nanosatellite payload. The use of parallelism approach to achieve low energy consumption ensures high processing efficiency. Up to 12 signals can be decoded simultaneously. Control of operating points provides savings up to 43% in the dissipated power and 12% in the energy consumption. The implementation proposed has a simpler architecture than the one presented by EDC. Results show that this implementation presents savings of up to 75.7% in power consumption. Thanks for your attention. Any questions or comments can be sent to rafael@ufrn.edu.br.
Thank you for the presentation. Is Rafael here? I don't think so, right? Is there one of the authors that's here? Okay, so we'll miss the Q&A for this paper, since none of the authors is here. So let's move to the third presentation, which is a middleware for system consumes Ethereum data in soft real time, a semantic web approach. This paper is going to be presented by Célio Márcio Soares Ferreira.
Hi everyone, my name is Célio. I'm a Federal University of Ouro Preto PhD candidate, and I will present the paper, A Middleware for a System Consumes Ethereum Data in a Software Real-Time, a Semantic Web Approach. Okay, Atli blockchain advances in a journey beyond its original use case, the cryptocurrency applications. The reason is a strong disruptive characteristics like cryptography and its decentralization network. And the new disruptive use case, mainly in Smart Series and Industry 4.0 IoT app, have used benefits of on the blockchain reliability and the resilience feature. And an important actor in this scenario is Ethereum. Ethereum is on the leading blockchain to developing apps using mainly smart contracts and already is called the world's computer. And Ethereum community path independence of the centralized characteristics of the internet and try reinvent it in an ecosystem called Web3. Ethereum today is one of the leading platforms for deploying the so-called decentralized application of dApps. The recent popularity of the smart contracts development led the Ethereum to the leading development platform of new tokens, non-fungible tokens, and Oracle dApps. Now it's possible to see new proposals far from the domain of the financial applications, as IoT application in logistics and supply chain tracking. Okay, there are many propositions, API, and techniques to extract Ethereum data, but there isn't a standard to link its data. The excellent relevance of the Ethereum on the blockchain ecosystem motivate new research strategies of extraction and linking Ethereum data in a standardized way with the current dataset. We problem in this research is link and extract Ethereum data and current web data in a standard way. Okay, and one proposal to standardize models and integrate web data is the semantic web. Semantic web uses ontology models to allow query data using SPOCL and endpoints to allow dataset linking. Semantic web was proposed originally to simplify the consumption of the web data, allowing integration and cooperation with machine. Okay, and this work presents our thoughts to apply semantic web techniques to extract and link data to an Ethereum blockchain ecosystem, proposing data access standardization for applications that use Ethereum and smart contract as the dApps. It's allow, for instance, the link with the pre-exist dataset and the Ethereum data. Our work contribution is at Estras, a new ontology, and a middleware web developed as a proof of concept extraction software real-time data of Ethereum used at Estras ontology. Okay, and the idea of the @Estras ontology is add new components to @on, an important Ethereum ontology found in literature. In this figure, we can see @Estras and @on in action, using the classes and attributes that facilitate the understand and relationship between Ethereum entities. And this triple, we can see a external link with the DBpedia dataset using properties of the @Estras has an external reference. Okay. This figure shows an URI of WebMiddleware. This is a N-triples RDF format and represent a Ethereum transaction on Ropsten, a Ethereum testing network. This figure this URI use @on and @Estras ontology, and this URI is an SPOCL endpoint and can be used for visualization, query, and relation with another semantic web dataset. So I reached the end of my presentation, and I hope you enjoyed this paper. Thank you very much.
Okay, Célio, thank you for the presentation. I think Célio is here to answer questions. Is there any questions from the audience?
I'm here, José.
Okay, great. I have a question for you, Célio.
Okay.
How does your work applies to other cryptocurrencies? Is it possible to use other cryptocurrencies?
In a moment, I only research in deep in Ethereum because Ethereum is one of the main platforms to smart contracts, and cryptocurrency is the second. Is relevant on only the platform Ethereum. The cryptocurrency is used only, for instance, to count the cost of the smart contracts run. It's not relevant Ether, for instance, or Bitcoin or another blockchains. This work is the main contribution is extracting Ethereum, because Ethereum actually leads to one of the main platforms to develop smart contracts. And the relevance in Ethereum today is very grateful because the Ethereum communities improves a lot of researches and improves a lot of contributions in the softwares, and the GitHub, for instance, have a lot of pieces in the smart contracts and a lot of software too.
Do we have more questions from the audience? Is there another question? Thank you for your answer, Célio.
Okay, thank you for asking. Thank you, José. Thank you for our attendance.
Okay, if nobody wants to ask more questions, so I think we can move to the fourth paper, which is performance analysis of machine learning-based systems for detecting deforestation. It's going to be presented by Michel Araújo.
Hello, my name is Michel de Araújo, and I'm a master student at the Department of Computing in Universidade Federal Rural de Pernambuco, and today I will present a paper entitled Performance Analysis of Machine Learning-Based Systems for Detecting Deforestation. Here you can see this presentation agenda. We start by a brief introduction to the paper, followed by the experimental methods, where we'll discuss the data structure, the computational platforms, and the algorithm used, as well as the experiments. We then head to the results section and conclude the presentation with the conclusion and the future work. So let's start from the beginning. Machine learning-based image classifiers have played an important role in detecting deforestation, illegal mining, or fire. And as Brazilians are vast, and the scale and intensity at which illegal deforestation occurs grows every year, it is necessary to use tools capable of responding quickly to these situations. Several works have demonstrated the effectiveness of machine learning algorithms for remote satellite image classification. However, to the best of our knowledge, none of the existing works have considered the difference in performance of these algorithms on edge and server platforms. Our paper brings three main contributions. The first is that our experimental study shows that it's possible to use low-cost computational environments to perform image classification and help to protect the Amazon rainforest. And the second is that we experimentally showed a relationship between image size and algorithm performance with respect to the image classification. And last but not least, contrary to our expectation, deep learning algorithms like the CNN can be used on edge computers with good performance and high classification accuracy. For the experiment, now let's talk about the experimental methods. For this experiment, we used a dataset from a 2017 Kaggle competition. This dataset consists of a bit more than 40,000 images with 256 pixels in size. Each image can be classified with one or more of 17 labels, and the dataset was split into the ratio 80 by 10 by 10, 80 10 10 for training, validation, and testing. Platform data structure. Here is a sample of image and labels of some images. Here is a sample of some images and their labels. platforms. We adopted two platforms for this experiment. The first is a server that's a personal computer that simulates a remote server that receives and processes data from an edge computer. And the second is a edge platform that consists of a Raspberry Pi Model 4 and simulates a programmable drone that can execute machine learning algorithms. And here we can see a summary of the platform hardware configurations. Algorithms. We use three different algorithms of different types in this experiment. The first is a comparison-based algorithm, the k-nearest neighbors classifier. For the KNN, we use the k-neighbors parameter and found the best values of 18, 15, 25, and 19 for each one of the image sizes. The second algorithm was the rule-based handle force classifier. For the handle force model, we use only the number of estimator as parameter with values of 100 and 500. The last is a deep learning algorithm, the convolutional neural network. For the CNN, we created the threshold parameter. This parameter is used to fine-tune our model to our needs. The experiments. The first part of the experiment was to train all three algorithms on the server platform. The algorithms were trained with the following image sizes: 8, 16, 32, 64, and 128. And the models were then evaluated on the validating test set that is about 4,000 images, and the following evaluation metrics were obtained: accuracy, precision, recall, and F1 score. The average classification time was also collected for the server and the platform. And now let's check out the results. While training the KN model, we found that the best values for the key neighbors being 18, 20, 60, 15, 25, and 19 for the image size of 8x8, 16x16, 32x32, and 64x64 respectively. And the precision metric had little variation considering the image sizes, and the recall presented a non-monotonic behavior, and this was expected. This is an expected result since the KNN is a comparison-based algorithm, and adding more pixels to the image is like adding a new feature that's almost equal to the other features, and it does not increase the data quality. And the classification time results for the KNN, the average classifying time for the two platforms is very close for the KN model, but the Edge platform was not able to load the k-nearest neighbors model for the 64x64 image size. For the RF model, the RF model presented similar behavior to the KNN. The image size did not show a clear relation with the adopted evaluation metrics, and this result can be explained considering the rule-based algorithms are well optimized for multi-feature data, and images have one feature, that is the pixel value, and adding more pixels to the image will not reflect on major improvement on the model. As you can see, in the classification timing and the classification time results for the handle forest, the performance difference between the two platforms for any trees, the number of trees equal to 100 is almost 0, and for the number of trees equal to 500, the average classification time is much bigger. And for the CNN model, our experiment shows that the image size has positive relationship with the algorithm evaluation metrics for the CNN. As you can see, the bigger the image is, the better is all of the evaluation metrics. As you can see, the threshold equals to we can set the threshold to the value to get given maximum value for the recall metric, and therefore we choose the threshold equals to 0.3 because it gives a high value to the recall but a not so low value to the precision, since these two metrics are inversely correlated. And the classification time results for the CNN, in average, the edge platform is 0.67 times slower than the server, and as the image size increases, the server platform performance approach the edge performance. And conclusion, in future work, we have two main conclusions of our work. The first one is that our experiment study revealed that machine learning-based image classifier are a valuable solution for monitoring deforestation, even when using low-quality images and resource-constrained edge devices that can be used in a drone-based systems. And the second conclusion is that considering the trade-offs between average classification time and evaluation metrics, mainly recall, the CNN had the best cost-benefit among the tested algorithms for the edge platform, thus being a good option to be deployed in edge computers. For the future work, we plan to consider some environmental factors, such as status of wireless communication link, the battery usage, and the interference from other processes. Thanks for your time. That's it. Thank you for your time.
Thanks, Michelle, for the presentation. I think Michelle is here, right?
Yes, I'm here.
Okay, great. Is there any questions from the audience? You can type, or I have a question, Michelle. At the beginning, it was not clear for me how, because the title of the paper mentions deforestation, but you presented a classifier that have, I think, 17, right?
Yes.
Classes. How do you map these 17 classes to measure deforestation?
Yes, we have 17 different classes, and 2 of them are related to deforestation. And yes, we focus on a binary classifier. So if we have one of these 2 classes that are related to deforestation, we have a yes, and if you have the other 51 ones, we have no deforestation.
Okay, I understand. Do we have more questions? Any other question? If not, I have another question. Okay. I thought that 2 things are different in your paper. I never saw anyone using random forest for image classification. Why did you do that?
It's because it is our, how can I say it, is a very common algorithm for another task, like regression or classification that are not related to images.
Yeah, but they're not for images. Yeah.
So I thought it is to use and it's fast, so why I can give it a chance to try it. So I read one of 2 papers that the author did that, and the result was good. It's not like the CNN, but it's okay. So I think that I could try one.
Okay. And my last question would be: you only said CNN, but you didn't present any details about the architecture of the neural network. Could you please give us some details about which was the model that you have used?
In the paper and in the presentation, I said that I used the VGG architecture. And in the paper, I said that it was something like we have three layers, three blocks of layers. So I have one convolutional. If I remember well, it's one convolutional, one max pooling, and another one that I can't remember right now. But we have something like that. We have 3 times this block of operations. And the image, the sizes of these operations relates to the image of the size of the image. It's not a fixed value.
Okay. Are there other questions from the audience? If not, I think we can move to our. Thanks, Michel, for answering the questions.
Okay, thank you too.
I think we can move to the 5th paper, which is analysis of the feasibility of remote access to industrial wireless networks by means of VPN. Rodolfo is going to present this work.
Hello everyone, my name is Rodolfo Bruno Recht. I'm going to present this work called Analysis of Feasibility of Remote Access to Industrial Wireless Network by Means of VPN. In 2018, the National Confederation of Industry in Brazil tabulated a survey that 48% of industrial leaders intend to invest in digital technologies in the coming years. In 2021, this trend continues. Industries such as oil and gas, coal, minerals, wind farms, water treatment need remote monitoring and control. I will present a solution for remote communication for field device from a wireless HART network to apply a methodology to analyze the latency characteristics of this communication. The scheme in the figure represents remote VPN access via Internet to an industrial network with a wireless HART gateway and connected field device. Figure 1 shows the proposal overview. To access the field device, the remote host uses a connection through a virtual private network, zero-tier, accessing the gateway. Capturing the communication latency is done using different methods. To measure the step shown in Figure 2. This slide also lists the locations that have remotely accessed the wireless HART network. A script written in Python was developed to capture the latency time per segment. The latency calculation in this thread occurs by the difference between the clocks of the local and remote host at the time a command is sent. To achieve good accuracy, at each capture cycle, these hosts are synchronized with an NTP server. In this step, it was necessary to use ping command from the local host to the gateway. This was necessary as the gateway is an industrial equipment that does not allow access to its firmware. The result time in milliseconds collected by the ping command is divided by 2 because the ping command measures round-trip time of the data packet. Special modify command 130 and 131 carry the value of ASN. The ASN, absolute slot number, is a number of cycles of the gateway with a period of 10 milliseconds. ASN values are collected when a command is received by gateway and when received by field device. The difference of ASN values of these moments inform the latency occurred in these segments. Figure 5 and 6 shows the communication latency capture scheme for this segment. Figure 7 shows the complete sequence developed in Python to capture the latency value in remote access to the industrial network. Two case studies were considered. Figure 8 shows a wireless HART network with field device communicating directly to the gateway. In this case, the latency was statistically analyzed with this topology. The most relevant segment in total latency was also analyzed. Figure 9 shows the wireless HART network with a field device communicating indirectly to the gateway. In this case, the latency with this topology was statistically analyzed. Figure 10 shows the latency interval for each remote access location. Table 1 shows the number of samples considered, mean and standard deviations values for each location. The table 2 shows that the most significant latency value and within the wireless HART network. The least significant latency value is within in the local network. The table 3 shows the statistical analysis of latency measurement from the original topology to the new topology. The comparison shows that the topology change has significantly impacted latency within the wireless HART network. The conclusions are: all locations had statistically different latency interval. For remote monitoring and control on device in a wireless HART network, latency intervals must be smaller than the latency parameters supported by the system. The segment with the most relevant latency is the gateway to field device, while the local network has negligible latency in relation to the total latency. Future work can complement the latency analysis tools with other monitoring methods. Thank you very much.
Thank you for the presentation, Rodolfo. Do we have questions from the audience? No questions. I have a question for you. You used a HART protocol in your experiments. Are there other options of industrial protocols that can you compare with that would be better, would present better results, or other options that you could have choose? Rodolfo, o que eu estou perguntando é se você usou HART, né? E se você teria outras opções de protocolo para poder utilizar, por que você escolheu HART? E se teria outros protocolos que poderiam ser mais adequados para esse trabalho.
Ok, eu escolhi HART porque o laboratório dispunha de gateway HART e nós conseguimos então fazer os comandos HART serem enviados diretamente para o gateway sem precisar acessar a web, não sendo direto de um comando, de um script Python, né? E conseguimos modificar alguns comandos, esses dois comandos que foram apresentados, de tal forma que eles pudessem nos devolver a variável que o gateway que o gateway gera ciclicamente, o ciclo dele, para que a gente pudesse analisar esse terceiro trecho, que é o mais complicado, onde a gente calcula o ASN, o Absolute Slot Number, no momento que chega o comando no gateway e depois no momento que o field device responde. Então, com essa diferença, nós podemos saber qual é a latência naquele tipo de rede, mas não analisamos outros protocolos.
Okay, Rodolfo, thanks. Are there more questions from the audience? No more questions? So thank you again, Rodolfo, for answering the question. I think we can now move to the last paper of this session, which is deep learning based visual odometry models for mobile robotics, which is going to be presented by Frederico Souza.
Hello, everyone. My name is Frederico, and I'm from the Federal University of Ouro Preto. And I'm going to introduce you deep learning-based visual odometry models for mobile robotics. In our introduction, we're going to talk about what is odometry and the different ways to measure it. So odometry is a common problem in navigation systems where we need to estimate a vehicle's position in a given environment. This can be useful to perform tests such as autonomous navigation and obstacle avoidance. So in these tests, you'll need to contain and preserve information about the vehicle's position and orientation in the space to avoid other robots or to perform other autonomous tasks and so on. There are different techniques and sensor types to measure odometry. We've got GPS, we got visual odometry that's done mostly through cameras, we got wheel odometry, laser odometry, and odometry through IMUs. So each of these techniques and sensor types, you can even fuse them to get better odometry, but they all have an associated cost, both computationally or financially. It can be expensive to fuse all this data to gather all the needed sensors to have a reliable odometry. So in this work, we're going to measure mobile robots' odometry with only a monocular camera. And we're going to do this through a deep learning based approach. So we train a neural network to relate an image to a given position on an environment. So we're going to measure odometry in a domestic or industrial scenario where multiple robots will explore the same environment. We're going to explain further our methodology, how this is going to work. So for our references, the main two aspects of our reference are mobile robotics and edge AI. On the edge AI side, we've got Wang, Madzia, and Klippel all showing that we are every time more needing more processing power at the edge in cases where you can't reach the cloud for processing these neural networks. While Quingley and Sid, they highlight the main advantages of using ROS, which is the Robot Operational System, to build mobile robots. So for our methodology, we developed a robotic platform with SLAM capabilities, and SLAM is simultaneously location and mapping. This SLAM algorithm that we're going to use is going to feed the neural network that we're going to use, as we show here. So we propose a visual odometry approach using deep learning. So we trained a neural network to relate an image of the monocular camera, which that monocular camera we're going to capture, to a given position on this map that we mapped through a SLAM algorithm. And so here is our workflow where we're going to need a first robot equipped with a camera, a LiDAR sensor, and an IMU to map the domestic environment with a SLAM algorithm. So once we get this mapped this map that we obtain through navigating the environment with the robot. We teleoperate the robot through the environment. Then we build a data set relating the images and a position and orientation data from this lane algorithm. So this data is used to train a neural network to relate the images with a given position in this mapped environment. So we do this to achieve multiple robots equipped with only a monocular camera can have an odometry inside this environment. So we collect this ground truth, fixing a starting point for the robot, and we teleoperate the robot through this domestic environment, and we get the data for the neural network. We're going to talk about some results that we got in this approach. So we evaluated 3 models according to an Euclidean distance between the prediction and the ground truth of our network. So as we can see, the ResNet 15 model had the better result, which is the mean error, the smallest mean error. And also we use a standard deviation to see if the errors are too different from each other. So this is the table where we show that the mean error of the ResNet model was 45 centimeters approximately. We also evaluate these models through a scatter plot where the blue points are the prediction points and the red points are the ground truth points. And this is our custom model scatter plot. This is the second VGG16 model. And this is the ResNet 50 model. We need, in this approach, to the blue points adjust right where the red points are. So if they are too apart, it means that they're not aligning too well and the regression is not quite working. So as the ResNet 50 model had the best results, we further evaluated to see if it was actually making sense. So we have an histogram of the ResNet model that shows that mostly of our errors are below our mean error. We also have a box plot to see the distribution of our error, and it also shows us that we are below, most of our errors are below our mean errors. So to conclude this work, we presented an approach to visual odometry through deep learning techniques, where our best model, a ResNet 15 model, corresponds having an average error of 45 centimeters, which corresponds to 10% of the biggest distance on our environment, which is 4.5 meters. Thank you. This was our presentation.
Thanks for the presentation, Federico. Are there questions from the audience? I see Frank is still here. Yeah, he's still here. I have a question. Could you please give us...
Jose, your microphone is very bad. Could you try again? No, could you reconnect? Still turned off.
Can you hear me?
Yes, now.
Okay, great. So thanks, Federico, for the presentation. Are there any questions from the audience? I have a question, Federico. Could you please give us more details about the hardware that you used to run this?
To run the models?
Yes, I understood that the hardware is embedded in a robot, right?
Yes, yeah, we use a Raspberry Pi 4 on this.
Okay. And about the custom model that you mentioned, which was it? And why did you choose the custom model?
The custom model is a basic CNN. It's just some convolutional layers, and we try to build this model for less complexity compared to a ResNet or a VGG, and to see if the result would be better or worse, and to play around with these configurations. That's why we use this custom model.
Okay. You used a less complex model. Okay. And I'm also wondering about your results. You mentioned that the accuracy was like 10% of the area that you. Do you have any related work? How do you compare this with the state of the art with other related work?
Yeah, I haven't found any related works that use the same approach as deep learning used for visual odometry. In future works, we're going to compare this approach with Visual 2 algorithm or something like that. That is, Visual 2 is an algorithm for odometry with monocular cameras. It doesn't use deep learning, but we want to do this comparison with other, in the same environment, of course, to make this comparison. But in the present work, we haven't done this comparison.
Okay. Okay. Are there any other questions from the audience? So, Federico, thanks again for answering the questions.
Thank you.
I think we are done now. We can close the session. I would like to thank you all for attending section 5, which is application and IoT. Thank you.